Imagine transforming the heart of cement production with a single innovation. Vertical raw mills have dramatically changed the landscape of cement manufacturing, promising both improved efficiency and reduced power consumption. Today, we explore how this technology is driving a revolution in grinding. Let's chart our journey through the world of vertical raw mills. We'll start with the fundamentals, uncover their unmatched advantages, compare them to traditional ball mills, dive into strategies for reducing power consumption, and finish with a real-world case study on optimizing fan efficiency. To understand the impact of vertical raw mills, we first need to grasp their core principles and essential parts. This chapter reveals how these mills operate and what makes them unique in cement production. Before we dive deeper, let's clarify what a vertical raw mill actually is. In cement manufacturing, a vertical raw mill is a type of grinding equipment primarily used in the cement industry to pulverize raw materials such as calcium carbonate, clay, and iron ore into a fine powder known as raw meal. This definition sets the stage for understanding its critical role. Here's how the vertical raw mill works, step by step, from material feeding to final classification. Material feeding involves delivering raw materials directly onto the center of a rotating grinding table. Grinding action is achieved as rollers apply immense pressure, combining compression, shear, and impact forces to break down the material. The hydraulic system adjusts grinding pressure based on material hardness and desired fineness, ensuring optimal performance. Hot gas introduction serves two purposes: drying the raw material and conveying fine particles upward for classification. The integrated separator classifies particles, allowing fine material to exit as product, while coarse particles return for further grinding. Notice how each component plays a distinct role in the grinding process, working together to maximize efficiency. The grinding table feeds and grinds the material, serving as the central platform for the process. Grinding rollers apply the necessary pressure to break down the material efficiently. The hydraulic system adjusts roller pressure, adapting to material properties. The separator classifies ground material, ensuring only fine particles exit as product. The nozzle ring directs hot gas flow, aiding in drying and material transport. The gearbox and motor provide the rotational power needed for the grinding table. The housing encloses the grinding mechanism, maintaining structural integrity and containing the environment. Let's trace the chain of events in a vertical raw mill, from material entry to product output. Material entry begins with raw materials entering the feed bin, setting the stage for grinding. The grinding table receives the material, rotating to distribute it for grinding. Roller pressure is applied, compressing the material and initiating the grinding process. Hot gas injection dries the material, preparing it for further processing. Separator action classifies the material, separating fines from coarse particles. Product output delivers the finished raw meal, ready for the next stage in cement production. Now that we've seen how vertical raw mills work, let's explore the advantages that make them a game changer for cement manufacturers. This chapter highlights why VRMs are preferred over traditional methods. Here's how vertical raw mills deliver energy savings and environmental improvements across multiple dimensions. Energy efficiency is a standout feature, with vertical raw mills consuming 30 to 50% less specific power compared to ball mills, thanks to material bed grinding. High drying capacity allows VRMs to handle raw materials with up to 15% moisture, using integrated hot gas for simultaneous drying and grinding. Integrated operations combine crushing, drying, grinding, and classification into a single unit, simplifying the process and reducing equipment footprint. Low dust emission is achieved through negative pressure operation, creating a cleaner working environment. Lower noise levels, typically 20 to 25 decibels less than ball mills, improve workplace conditions. Let's look at how vertical raw mills improve product quality and reduce maintenance needs, making them highly adaptable. Consistent product quality is ensured by closed-circuit grinding, which maintains stable chemical composition and uniform particle size. Low wear and maintenance result from grinding rollers not directly contacting the table, and accessible designs simplify upkeep. Operational flexibility allows VRMs to quickly adapt to changes in material characteristics and production requirements. To appreciate the leap in efficiency, we need to compare vertical raw mills with the traditional ball mill. This chapter lays out the differences that matter most in cement production. We're comparing vertical raw mills and ball mills across several shared attributes to reveal their strengths and weaknesses. For grinding principle, vertical raw mills use compression, shear, and impact on a material bed, while ball mills rely on impact and attrition by grinding media. Energy consumption is significantly lower in vertical raw mills, with 30 to 50% less specific power, compared to the high consumption of ball mills. Drying capability is excellent in vertical raw mills due to integrated hot gas, whereas ball mills are limited and require separate dryers. Footprint is compact and integrated for vertical raw mills, while ball mills need larger space and multiple units. Noise level is lower in vertical raw mills, typically 20 to 25 decibels less than ball mills, which are much louder. Dust emission is minimal in vertical raw mills thanks to negative pressure operation, but ball mills have higher emissions due to positive pressure. Product fineness control is excellent in vertical raw mills with integrated separators, while ball mills are good but often need external separators. Wear rate is lower in vertical raw mills, reducing maintenance needs, while ball mills experience higher wear. Maintenance is easier in vertical raw mills, with longer component life and easier access, compared to the more complex and frequent media replacement in ball mills. Reducing specific power consumption is the ultimate goal for efficient grinding. This chapter presents actionable strategies that operators can use to optimize vertical raw mill performance. Here's how operational and mechanical optimizations can significantly reduce specific power consumption in vertical raw mills. Dam ring height optimization stabilizes the material bed, preventing vibration and ensuring efficient grinding. Grinding roller pressure tuning matches the pressure to material hardness, avoiding unnecessary power consumption. Nozzle ring area adjustment maintains ideal air velocity, reducing the load on the mill fan. Timely liner maintenance preserves the effective grinding surface, keeping efficiency high. False air sealing prevents leakages, reducing the workload on the mill fan and saving power. Separator vane angle optimization minimizes bypass, ensuring that fines exit the mill instead of returning for unnecessary regrinding. Precise water spray management controls vibration without increasing the drying load, which would raise fan power requirements. Feed size control maintains a uniform particle size distribution, allowing the mill to operate smoothly at peak efficiency. Hot gas duct design minimizes sharp bends, reducing pressure drops and lowering resistance for the process fans. Maintaining the feed bin level prevents false air entry, keeping the mill's internal atmosphere stable. Electrical and automation upgrades further enhance efficiency, targeting the largest power consumers and optimizing control. Installing a variable frequency drive on the mill fan allows precise airflow management, reducing power consumption. High-efficiency motors, such as IE3 or IE4, reduce electrical losses and improve overall efficiency. Expert control systems using AI or fuzzy logic eliminate human error, keeping the mill running at its optimal point. Differential pressure monitoring keeps the mill DP within a tight range, avoiding excessive internal circulation and fan power loss. A variable frequency drive on the separator motor matches product fineness requirements, avoiding overspeeding and wasted energy. Process and strategic improvements round out the toolkit for reducing specific power consumption, ensuring every aspect is optimized. Strategic use of grinding aids improves material flow and prevents coatings from forming on the grinding table. Optimizing circulating load balances rejects and fines, preventing the mill from being overloaded or underutilized. Moisture control in feed material manages the drying load, using covered storage or pre-drying techniques. Mill start-stop optimization minimizes frequent trips and restarts, reducing peak power consumption during startup. Regular energy audits pinpoint leaks and identify areas for further optimization, both thermal and electrical. To bring these strategies to life, let's examine a real-world case study. This chapter shows how optimizing circuit pressure drop and fan efficiency delivered measurable results. Imagine facing a persistent challenge, a vertical raw mill running with a circuit pressure drop of 150 millimeters of water gauge, forcing the process fan to work overtime. This real-life problem highlights the importance of aerodynamic efficiency and sets the stage for a technical intervention. Here's how the technical intervention unfolded, step by step, to address the high circuit pressure and improve fan efficiency. Guide vane installation inside the cyclone outlet ducts straightened the vortex flow, reducing turbulence and exit losses. Pressure energy recovery converted rotational energy into linear pressure, minimizing kinetic energy loss. Balanced flow distribution ensured a uniform velocity profile in the discharge ducting, lowering back pressure on the grinding circuit. Notice how the intervention led to measurable improvements in circuit pressure drop and fan power consumption. Circuit pressure drop decreased from 150 millimeters of water gauge to 110 millimeters of water gauge, a reduction of 40 millimeters of water gauge. Mill fan power consumption dropped from 2,450 kilowatts to 2,240 kilowatts, saving 210 kilowatts. The return on investment and long-term benefits of this intervention extend beyond immediate energy savings, impacting overall efficiency and equipment longevity. Annual energy savings are substantial, with a direct power saving of 210 kilowatts per hour over 7,000 operational hours. Specific power consumption was significantly reduced, lowering kilowatt-hours per ton of raw meal produced. Fan life cycle improved due to reduced load, resulting in lower operating temperatures and less mechanical stress. The journey of vertical raw mills is a testament to how technical innovation can reshape an industry. By optimizing grinding processes and reducing power consumption, cement manufacturers are paving the way for a more sustainable and efficient future. The vertical raw mill stands as a symbol of progress, inspiring continued innovation.